Hello, welcome to this video. Today we're going to prove a cool property with matrices. So I assume that you know about matrices and are pretty comfortable using them. So let's look at our definitions. So first of all, if A is a matrix of size m by n and B is in size n by m, then if you know matrices, you should know this. The matrix A times B is of size m by m, and the matrix B times A is of size n by n. It's important that we define it that way, otherwise it literally won't be defined for our purposes. Next, let's look at the definition of a product of matrices. So the term in the matrix A times B in row I, column J, is the sum, as P goes from 1 to n, of the term in A on row I, column P, times the term in matrix B in row P, column J. And the n here comes from the sizes of A and B. A is of size m by n, and B is of size n by k. This is not a definition, it's a property that we'll prove. And this is the definition of the trace function for matrices. I shouldn't say function. The trace of matrices. So if C is a square matrix of size k by k, then the trace of C is the sum, as I goes from 1 to k, of the terms in C in place I and I. So in row I, column I. So it's basically just going on along the diagonal and summing all those terms. Now the property that we want to show is that for all matrices of these specific sizes, A from size m by n, and B from the opposite size n by m, that the trace of A times B is equal to the trace of B times A. So that is what we want to show. But first thing we'll do is prove this property. Okay, so first we're gonna prove this property in a more intuitive way rather than a formal one. So the first thing we're gonna do is look at, let's set a matrix of A of size m by n, such that the term in the matrix A in row I, column J, is the same as what we have in this term, I, J. So now let's look at our matrix. Let's actually literally look at it. So we will have A11, A12. That is our matrix. Now let's see what these sums actually mean in our matrix. If we look at the left hand side, we see that this sum, first, the sum j goes from 1 to n, is basically counting all of the sums, and it means that we look at the row number I and we sum all the numbers in it. So AI1 plus AI2 plus AI3, and so on and so forth. And this outer sum, the sums I goes from 1 to m, sums all the rows in which this happens. So we're summing all of the rows, and for each row, we're summing all of the terms in it. So what we're doing is summing all of the terms in the matrix in this left-hand side. In the right-hand side, what we're doing is first, instead, looking at the sums of the columns. So this is the sum of column J, all the sums in it. And then we're summing that for all columns. Meaning that, again, we're summing all the terms in the matrix. Either way we put the sums, we're summing all the terms in the matrix, meaning that these two sums are equal. So this is more of an intuitive way to see why this is true. Now let's go back and prove our property. Okay, now let's prove our property with the trace, the trace of a matrix. So let me first quickly explain why we actually need the sizes of A and B to be sort of opposite to each other. Well, to take the trace of a matrix, we first have to make this matrix a square matrix, and that only happens if if this is in this formation, A is of size n by n and B is from size n by n. And another thing that we need is that both A and B and A to be defined. AKA, if A times B is defined, then the amount of columns in A is equal to the amount of rows in B, that's n and n. And if B times A is defined, which it needs to be, then the amount of rows in A needs to equal the amount of columns in B, m and m. So in both cases, what we need to be defined is defined. So this is what we need. In any other case, where, for example, this is n by k, and k is different than m, but this is not going to happen. So, quick explanation for why these need to be of these sizes. Now, let's get on with the actual proof. So, the proof is not a very exciting proof. It's algebraic proof, but it gives a nice, cool result. So let's see. First of all, if we look at the trace of a function, again, what it is this sum right here. And and A times B is of size n by n. So this is first the sum as I goes from 1 to m of AB, the matrix AB, when it's row I, column I. Which now, let's look at the definition of a product of matrices. The product, in this definition, the product, the term in the matrix, A times B, in row I, column J, is just this sum. So, let's just substitute it in. So this is the sum as I goes from 1 to m. Now instead of P here, we're going to instead put in J. It doesn't matter what the term is, as long as we didn't use it earlier. So it doesn't confuse anything. So we can say that this is the second sum. The inner sum is of J as it goes from 1 to. Now here we have n. So to what parameter does it go in our case? Well, you can see that it goes to the amount of columns in A, which also is the amount of rows in B, which is n. So this is the sum as J goes from 1 to n. So this is the sum as J goes from 1 to n of, now let's say we have A of IP. P is J here, so this is A at IJ times B when it's at PJ. So this is, but J here is I, again, because we're looking at the term in row I, column I. So J here is I. So this is B in row J, column I. Now, this is what we know. This is the left-hand side. This is the trace as A. This is the trace of A times B. So now let's look at the trace of B times A. So this is the sum. Now the parameters themselves don't matter. So we're going to do instead that J goes from 1 to what? Well, B times A is a matrix of size n by n. So the sum goes to n of the matrix B times A at row J, column J. Now, let's use our formula of a product of matrices. So this is the sum as J goes from 1 to n of, now again, the parameters themselves don't matter, so instead of P, we're instead going to write I. So this is the sum as I goes from 1 to what? Well, because it's B times A, it needs to be the amount of columns in B and the rows in A, which is M. So this is the sum as I goes from 1 to M of what? Now, this is the place of the term in matrix B in row J, column I, because instead of I here, we have J, and instead of P here, we have I. So this is the place. Instead of A here, we have B. So this is the term in matrix B in row J, column I. And now we have sort of similarly, instead of B here, we have A. This J is actually J here, and P is I. So this is the term in matrix A and row I, column J. Now we can swap these around because they're terms in a matrix. They're scalars, they're numbers from our field F, which the terms in the matrix of the matrices come from. So these are scalars, so we can swap the product around. That's all right. And remember, by this property, we can swap these sums around. If we swap here the sums around and these terms around, we can swap the product, swap the sums as we've shown, and we'll get the exact same thing. So we actually know that these are the same thing. And because this represents the trace of A times B, and this represents the trace of B times A, we finally get our property that for matrices A and B of these sizes, we get that the trace of A times B is equal to the trace of B times A. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.